Welcome to Maths with EJD. Still talking about numerical analysis. We are switching gear to consider numerical solutions, numerical solution to algebraic equations, numerical solutions to algebraic equations. Okay. Now, of course, we know algebraic equations involve things like equations like lines and quadratics and all that. But our focus here is going to be based on systems of equations, like equations you have to solve simultaneously. And the methods are in two broad categories. So just like what we had for root finding, so we have methods in two broad categories. It can be either direct or iterative. So we have direct methods or iterative methods. So for the direct methods, the first thing we'll be considering is Gaussian elimination. Gaussian elimination. And that is the topic for today. I mean, for this video. And then after that, we'll be talking about LU decomposition. That's lower matrix, upper matrix decomposition. Then after that, we'll deal with Cholesky decomposition. Cholesky decomposition. And for the iterative methods, we have for the iterative methods, we have Jacobi method, Jacobi method. We have Gauss-Seidel method, Gauss-Seidel method. And lastly, we have successive over-relaxation. Successive over-relaxation. All right, so here our focus is on Gaussian elimination. Let's go for that right now. Gaussian elimination. Interestingly, I've done this before in the matrix playlist, so you can still trace that. But I mean, for the sake of this, I'm going to take one example. But if you want deeper understanding of the whole Gaussian elimination and other things related to matrices, you can see that under the matrices playlist. That was the very first playlist I started this channel with. So Gaussian elimination is a direct method. It's a direct method for solving systems of linear equations. For solving systems of linear equations by transforming the coefficient matrix into an upper triangular form, and then performing back substitution to find the solution. Okay, um, for the sake of time, I'll just go straight. Instead of setting any theoretical background, I'll just use the question to explain the background. Imagine this example. Solve solve x plus 2y plus 3z equals 9. Then 2x plus 5y plus 6z equals 18. And finally, 3x plus 6y plus 14z equals 30. Okay, so we need to solve this. Of course, to solve this means to look for x, y, and z. All right, so um, as for the solution, we have, so I mean, the first thing we want to do is Gaussian elimination, just like we said, right? Gaussian elimination is a direct method for solving systems of linear equations by transforming the coefficient matrix into an upper triangular form. So it means we need to get this in matrix form. So if to translate this into matrix form, we simply have 1, 2, 3, then 2, 5, 6, 2, 5, 6, and then 3, 6, 14, 3, 6, 14. Okay, and then we have x, y, z, and that is equal to the right-hand side, 9, 18, and 30. So that's what we have. Now the deal is to so this is what is known as the coefficient matrix. So the coefficient matrix, and this is the, should I call it the solution matrix? So uh is it should I think I'll just call it the right hand side, I'll just call it the right hand side for now. Of course, these are the uh variables. These are the variables we are solving for. Now, again, the definition says the element it's a direct method for solving systems of linear equations by transforming the coefficient matrix into an upper triangular form. Upper triangular form. So before we do that, before we transform to upper triangular form, the first thing we want to do is we want to make it into an augmented matrix, transforming into an augmented matrix. So it means we have 1, 2, 3, 2, 5, 6, 3, 6, 14, 3, 6, 14. So augmentation means we now put the right-hand side by the side uh, to make it into a 4 by 4 matrix, into a 3 by 4 matrix now, right? So this now, we bring the right-hand side, 9, 8, 18, 30, 9, 18, 30. So this is what is called the augmented matrix. Now, we want to now make this matrix into a an upper triangular form. And what that simply means is that we need to, so we look at the principal diagonal. I think this is better. So this is the principal diagonal. Okay. If you start from the row 1, column 1, row 2, column 2, row 3, column 3, that's the principal diagonal. Now, everything below the principal diagonal, 2, 3, 6, all of these have to become 0. So once you make all of those into 0, then it is now easy to find the solution. All right. So our goal is to make all of these things into 0, and make sure everything along the principal diagonal is, say, it doesn't, those ones do not have to be 0. Okay, everything below that line should be 0. That's the deal here. Okay, so every other thing we want to do now is to make sure that happens. So let's go ahead and say this. Um, transforming into upper triangular matrix, upper triangular matrix. We proceed as follows. So, of course, we can see this is row 1, row 2, and row 3. So work with the rows like that to get, so the goal is to make row 2, column 1, row 3, column 1, and row 3, column 2 into zeros so that we can now find the result for X, Y, and Z. So that's the goal right here. So, and the way to do that is, thankfully, um, from here now we see that this element in column one, row one, column one, is we can take that as the pivot. So as the pivot now, we can take care, we can use that to make this into zero and this also into zero. So what we are going to have is this, that row one remains what it is already. Okay. Row one remains what it is because we already have we have one up there. And then row two, row two is going to become zero. And the only way that can happen is that the new row two is going to be the old row two minus 2 times the old row one, because if this has to be zero, um, let me see, is that what I should say? Yeah, yeah. So the old 2 minus 2, that's zero. So we'll go according to that order, and then we can get what we need to get. Okay. So, and then for row three, it's the same idea. The new row three is going to be the old row three minus 3 times the old row one, so that we can have 3 minus 3 times 1, that's 0. So let's go for that now and see what we get. Okay, so row one is 1, 2, 3, 9. 1, 2, 3, 9, like that. Then for row two, like what we have said already, so it's 2 minus 2 times each of these. So 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 9 is 18. So we're just simply going to have 2 minus 2, this 2 minus this 2. So we have 0 here. Then 5 minus 4, this 5 minus this 4. So we have 1. Then 6 minus 6. Interestingly, that gives us 0. And then we go ahead. 18 minus 18, another interesting 0. Okay, so we go to line 3. So now, okay, so I can put this at the top. So that's 3. So we said that should be row 3 minus 3 times row 1, right? So that is 3 times row 1. So 3 times row 1, that is 3. 3 times 1, 3. 3 times 2, 6. 3 times 3, 9. 3 times 9, 27. So we go again, and we have 3 minus 3. That is 0 down here. And we go up again. 6 minus 6. Another, interestingly, 0. Then we have 14 minus 9. 14 minus 9 would be 5. 14 minus 9, that is 5. And then the next one, we have 14. Oh, 14 minus 9 is 5 already. 6 minus 6 is 0. 30 minus 27, that gives us 3. Okay. I mean, it is interesting that in one sweep, we have everything we need. Like, so by just doing this straight, this is already in upper triangular form because everything below, in fact, normally if this did not give us 0 immediately, we would have had to do it again. But thankfully, we just have that in one sweep and we are good to go. So let's just move on and get the result. So now we can say, therefore, we have 1, 2, 3, 0, 1, 0, 0, 0, 5 multiplied by x, y, z, and that is equal to 903. So what that gives us is this. So if you multiply, all of these out, right, this is more like you have x, y, z in. So to multiply, I mean, if you go to my playlist of matrices, you'll understand what I'm trying to do here. So this x, y, z now, because this has 3 rows and this has 3 columns, I mean, this has 3 rows and this has 3 columns. So you have to invert it on themselves. So you have x, y, z, x, y, z, and x, y, z. So what I'm trying to do there is this. So with each of these x, y, z, now then you invert 1, 2, 3 over it. So this will be 1, 2, 3. Then the next will be 0, 1, 0, 0, 1, 0, and then again 0, 0, 5 for the last one, 0, 0, 5. Okay. And all of this will be equal to the 903 you have at that side, 903. So with this now, we have what we need. So we can say this is the same as x plus 2y plus 3z. Then coming here, this is just y is equal to 0. I mean, that's an easy one. Oh, sorry. This is just y, right? This is just y. X times 0 is 0. Z times 0 is also 0. Then we have y times 1 is 1. Then coming down, we have 5z, and all of this is equal to 903. So from here, it's already clear that we have x plus 2y. Guess I want to color code at this point. So I have x plus 2y plus 3z equals 9. Then we have y equals 0, straightforward. And then we have 5z equals 3, which implies that z is equal to 3 over 5. So this is one result like this. This is another result. But we need to get x. And interestingly, that should be easy because we have all this sorted. So this is so to find x, we just have x plus 2 times 0 plus 3 into 3 over 5 equals 9. And that will be x plus 0 plus 9 over 5 equals 9. So that is x equals 9 minus 9 over 5. So we can take the LCM, right? So x is equal to 5 here. 1 in 5. 5 times 9 is 45. So we have 45 minus 9 all over 5. So x is equal to 36 over 5. So we can conclude that therefore x is equal to 36 over 5. If you want it in decimal, we can get it, which is multiply top and bottom by 2 each. So that's 72 over 10. That is simply 7.2. Then we have y to be 0 already, and z is 3 over 5, like we had there. So 3 over 5, and 3 over 5, if you want it in decimal, that's 3 times 2, 6. 5 times 2, 10, that's 6 over 10, which is 0.6. And that is the result we are in for. So that's how to go about Gaussian elimination. Get your matrix, get your system of equations, write it in matrix form, then augment the matrix by imposing the right-hand side on it, and then turn it into an upper triangular matrix by making every element under the principal diagonal into 0, and then you could use backward substitution. So what we have done here, so what we did from this point down is what we call backward substitution. Backward, because you can start getting the values starting from Z. Backward, uh, backward substitution. Substitution. All right, so watch out for the next video, which is going to be, we are going to solve the same problem using the LU decomposition. That's another interesting approach. So if you have not subscribed to the channel, go ahead and do that right away and hit the notification bell so that you can get alerted when a new video is released. If you have subscribed already, thank you so much. Then you can comment, let me know how helpful these videos are. And of course, let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. Then like and share so that more people can have access to this. But before I go, let me try to formulate a practice question. You can try this practice question. So solve p plus, okay, it doesn't only have to be this, 2p plus 3q minus 4r equals, then I have let me say now I have say p plus q plus R equals, and then P minus 2Q plus 4R. So let me see. Just trying to formulate it now so you can have something to try your hands on. Okay. Is 3Q is 2, R is 4. Okay, that's 6 plus 6 minus 16. That is so this is minus 4. Okay. Let this be like this. Minus 4. Then this is 9. And the last one is 3 minus 6 plus 16. So this would be 13. Okay. So if you do that right, your solution should actually be that P is equal to 3, Q is equal to 2, and R is equal to 4. Okay. So, okay. Yep. Then 3 minus. Is this okay? P, that's 3 minus 4, that's minus 1. Minus 1 plus 16. Okay, this should be this should be 15, I think. Yeah, I think this should be 15. Final check. 3 minus 4 minus 1. Minus 1 plus 16, 15. 3 plus 2 plus 4, that's 9. 6 plus 6, 12. Minus 16 minus 4. Yeah, so try your hands on that and let's see, using Gaussian elimination, let's see how that works. Till I come your way again, keep enjoying maths. Bye.